last episode, we had discussed what was supposed to be the final version of Cerberus's VGA circuitry. I showed you the final prototype. But since then, I have been playing around with it, turning it on and off, and I realized that occasionally, not too infrequently, the image is just misaligned. You see, the first row of characters is wrong. These are the wrong characters. They are also misaligned. It's starting from the middle of a character instead of from the beginning. And this was a sort of a random problem. Sometimes it would happen, sometimes it would not. So suspecting that it might have something to do with the quality of the vertical and horizontal sync pulses, I improved the circuit a little bit with two filter capacitors, ceramic capacitors that you see there, and two current limiting resistors of 68 ohm. And that's where the signal, the sync pulses go to the VGA circuit. Now I tested each of the signals starting from the vertical sync pulse with the oscilloscope, and it's a perfect signal. It cannot be better than this in terms of shape, in terms of absence of noise. It's a fantastic signal. Even the frequency I measured and it was correct. Now moving on to the horizontal sync pulse to observe the quality of that one, and it's the same conclusion. All the measurements were right, the signal shape is perfectly alright, everything looks great about these signals, which sort of brought me to a loss, but I was not sure what to make of it. I even tested the phase relationship between the horizontal sync pulses in yellow and the vertical sync pulse in blue, and it's exactly what it should look like, two horizontal pulses within the period of a vertical pulse. Yet the problem was still there very clearly. I would power cycle the circuit, and every now and then nothing would come up. SKANK wouldn't even produce a clock signal. It would just brick, and I would power cycle again, and sometimes I would get different things upon power cycling. Not zero as you see now, but sometimes I would get a screen. But a different kind of misalignment. If you notice now, the first row of characters is different. And I would power cycle it again, and sometimes it wouldn't start, and sometimes I would get nothing there. Kavya wouldn't start instead of SKANK. So yeah, it was a difficult situation. Notice there that I got back to the previous state, but it's completely misaligned vertically. It's starting the first row from the middle of a character bitmap. It's the wrong character as well, which suggests that Kavya is not starting correctly. It's counters that control how many passes we've done in each character line, and tell the rest of the system in which line you are. Are you in the top of the character? Are you in the bottom of the character? That was starting wrongly, because the screen didn't start from the right place. So we seem to have problems with the SKANK and with Kavya as well. Neither seems to be starting when it's supposed to start, or to start in the state it's supposed to start. They are not being correctly reset, apparently. Now, since these chips worked perfectly before, I know that their design is alright, so I figured that there is something wrong with the layout of the breadboard. So I changed things around to shorten the wires and try to reduce the parasitics as much as I possibly could. But we still have the problem. You see the vertical alignment there is incorrect. So I moved on to a completely different breadboard, brand new, taken out of the box, moved everything there, and we still have the problem. Now there is no vertical misalignment, but the screen is starting from the wrong set of characters. And if I power cycle the system, I still get sort of unpredictable results upon each cycle, even if I wait for a while before powering it up again. If you notice, the first row of characters is different from what it was before. It's starting from 1 now. And then I power cycled it again, waiting for the capacitors to lose their load, and only then turning it on again. And look, now we are starting from 2 in the top line. So the system doesn't seem to have reliable, consistent behavior. I tried many other chips, identical chips programmed with the identical JDEC file, the identical design, and it didn't solve the problem. On the contrary, now each chip seems to have a preferred wrong starting point, and the synchronization is still not there. Some idiosyncrasies about each chip seem to be having an effect. Now, no two chips that come out of a manufacturing line are ever identical electrically. This is perfectly normal. If you try to make them identical, your factory would have zero parametric yield. There is a normal variation in electrical characteristics that are tolerable, and usually those variations have no role. They don't play any role in the functionality of the system. They work identically even though they are not identical. The problem is something is happening on this prototype that it's making these idiosyncrasies of different chip units, even when they are programmed with the same design, to actually have a visible effect, and that's what we have to figure out. Now, in a situation like this, what we have to do is to go back to the documentation, and there is an application note by Atmel, which is now part of Microchip. It has this title, and it explains the so-called power on reset, or POR, which uses a hysteresis effect. Basically, these CPLDs do not have a reset pin. They reset themselves when you power them up. So if this is the VCC signal, as it goes up and crosses a certain threshold, in this case this threshold here, which is labeled VRST, or voltage reset, that's the point where they will reset themselves, meaning that all state holding elements inside the chip, in other words, all the flip-flops, they will start with internal state 0. Their outputs will be 0 as opposed to a random number. Now, the tricky thing about this is that because I'm using these chips on a breadboard, the VCC power rail in a breadboard is very unstable. It goes up and down a lot because you don't have good power distribution, because you have a lot of parasitics. So your power rail may dip. And if it dips beyond a certain point, like here, it didn't dip far enough, so there is no power on reset. But if it dips beyond this threshold here, which is a little under the voltage reset, then it will reset itself, maybe partially, maybe some of the flip-flops will be reset and others will not, so you get very unstable behavior here. For this reason, I'm setting an option, large POR hysteresis, which basically requires that the voltage in the power rail goes down below 0.7 volts before you can have a power on reset again, which will happen here. So although the reset happens at VRST, the system has to start much lower than that for the reset to work. That's the hysteresis effect. So I'm using this option, but this brings some challenges of its own, because now when you turn off the system, you have to wait long enough for all the capacitors, including the parasitics, to discharge below 0.7 volts. If you turn the system back on before that happens, you will not get a power on reset, and the flip-flops will initialize in random states, 0 or 1s, and the system will go completely out of alignment, because a key design assumption is that all counters across Kavia and SKANK, all counters will always start at 0. If they don't, they will only keep on counting from that random point where they started, and everything will go out of alignment. Now, if we go back to the data sheet of the CPLDs, in this case is the 1504, I'm also using a 1508, but everything that you read here is applicable to the 1508 as well. There are several conditions listed that the design has to meet in order to guarantee correct power on reset or power up reset. Most of them are okay, but there is one tricky one, which is this one here, the first one. It says that the VCC power rail, the value in the beginning has to rise monotonically. And that's a keyword here. What does it mean for a signal to rise monotonically? Suppose you have the voltage here, the VCC here, and you have time in another axis. It means that as the voltage rises, it can never go down. It can rise sharper or less sharply, can even flatten out, but it can only go up. It can never go down. So here, if we make another graph, same thing, VCC is here, time is the horizontal axis. If it does this, poof, and then continues to rise, and then poof, and then has a little ringing and continues to rise. Well, each time that it goes down, here, here, and here, each time violates the monotonicity of the VCC rise. So if this happens, then there is no guaranteed power on reset, and the flip-flops will start with random states. And I think that's precisely what we are witnessing when we power cycle these devices, or even when we change one CPLD chip for another, programmed with exactly the same design, because those chips may have different residual charges, or they may have slightly different electrical characteristics, which is tolerable in any manufacturing line. It's just that in this case, because of this power up reset sensitivity, we actually see an effect from that. In fact, this condition here is also not trivial, now that I'm looking at it again. If VCC falls below 2 volts, it must shut off completely. So you have to wait for all the capacitors to discharge completely before you turn the device on again. Otherwise, it will not do a proper power on reset, especially on a breadboard with all the parasitics. This is also non-trivial. With a custom PCB where you have a ground plane connected to the multiple ground pins of these chips, the charge will be drained out quickly. But in a breadboard, that's not always the case. In fact, it's often not the case. So we actually have two conditions here that are not trivial to meet in a prototyping breadboard context. When you're using a breadboard, remember, each of these little columns here is a piece of metal, which is right next to another piece of metal, which in turn is next to yet another, and so on and so forth. And sometimes you may have, well, you certainly will have situations in which one of these little pieces is at a potential 0 volt, another one is at potential 5. And another one, maybe it's a potential 4, or it should be a 1, but it's at 4 instead of 5 volts. So what will happen here is that there will be a capacitive effect between these neighboring pieces of metal with different voltage potentials. And that is sure to happen. It's just that these capacitances normally are small, but under certain circumstances, like the sensitivity of the power on reset, this can be a problem. Now, you can visualize this as a number of tiny little capacitors distributed everywhere across the breadboard. So when you power on this circuit and you inject current in it, the first thing that will happen is that the electrons will migrate in order to charge these little parasitic capacitances first. That's the first thing that will happen. Only after these little parasitic capacitance are charged, only then will the ICs be charged. Now, even that is not quite right, because you will have a sort of random interplay of charges here. I'm illustrating all the capacitors with the same polarity because it's easier to draw, but they may be reversed polarities. So if you draw again that little curve of a VCC versus time, in a situation like this, full of parasitic capacitance, what you will have is that in the beginning, power will rise slowly because you're charging some of the capacitances. Then it rises a little faster, but then it faces some capacitances with reversed polarity somewhere else, and then it dips a little bit. And then it continues to charge a little faster, or maybe a little slower, and then dips a little bit, and so on. Now, each of these breaks in monotonicity here will prevent the circuit from having a proper, complete power on reset, and the two chips will initialize with random states, and therefore SKANK may not produce a clock, and Kavya may start counting not from 0 but from 5, from 7, from some other state, and everything will go out of alignment. I'm quite sure that this is what's happening. So to test out this hypothesis, I took SKANK out of the breadboard and put it on the development board from Atmel with in a proper socket, and connected it back to the breadboard via those cables that you see in there. And sure enough, SKANK always produces a Kavya clock. It never grinds to a halt. It always works. However, Kavya, which is still in the breadboard, still starts out of alignment. As you see there, the first line of characters is cut in half because Kavya started counting from the middle of the character, not from the beginning, not from the top. And it's also the wrong row of characters, so it didn't start addressing the video or the character memory or the video memory in this case, correctly either. So we still have a problem. We solved half of it, so the natural next step is now to do the same thing with Kavya to see if we solve everything. Okay, so I've moved Kavya to the little socket on the development board. This will make sure it's powered on and out properly. SKANK is still on the breadboard in its little adapter. I've done as much as I could to improve the circuit on the breadboard to make it more stable, more robust. I have installed 8 little pull-down resistors here to the inputs of SKANK that bring the character bits, well, the character byte from the character memory. I have also flipped SKANK around so I could use these breadboard jumpers to connect the output of the character memory, which are these 5 lines here plus these 3. They go there, and that's 1 byte of the character bitmap that goes into SKANK. I could do that with these little jumpers instead of those long cables that there were before that needed to reach the other side of the adapter. And this pull down resistors here for the character byte are meant to make sure that the character inputs to SKANK are never left undefined. They are never left floating. They should never float anyway. Yeah, just out of an attempt to prevent against anything unpredictable, I put this 3.3 kilo ohm resistors here as pull-down resistors. So if this memory is not enforcing the value of the byte, then the inputs to SKANK will be grounded, and everything will always be defined. What else did I do? I added one more capacitor to the power rails close to the amplifying transistor, which produces the, enforces and buffers the RGB signal. I'm using all 3 lines of the RGB signal now, so we should have white on the screen. And this is mainly supposed to smoothen out slower oscillations in the power line. And the oscillations caused by the switching of this transistor on and off due to the RGB signal are smoothened by this. I believe this is a 220 nanofarad bypass cap. I still do impedance matching with a 75 ohm transistor there, and there is a little pot. And these are the sync pulses, the vertical and the horizontal sync pulses. I am using a small, I believe this is a 68 ohm resistor. I'm using 2 of them between the output of the buffer and the cables that go to the VGA connector. And the reason is I just wanted to make sure that there is a current limiter between this chip and the connector, because I see how hard to drive this connector is, and I didn't want to drain too much current out of this little chip. So I have these current limiting resistors there, which also smoothen the signal. There are 2 filter caps. I believe one is half nanofarad or 500 picofarads, and the other one, I think it's 1 nanofarad. And they just smoothen out the high frequency jitter from the 2 sync signals. And there is another stabilizing capacitor here on the power line. And the buffer itself has a bypass cap as well. I installed this little 100 nanofarad or 0.1 microfarad bypass caps in key points in the power rails here, close to where the power is most needed. And if you are one of those who think a bypass capacitor is useless, have a look at that power rail signal that I'm measuring just on the power rail used by SKANK, one of them, and look at what happens when I insert and remove a little 0.1 micron bypass cap. That's without it. Now I'm going to push it into the power rail, and look at what you get. It's much cleaner. If I remove it now, it's a mess again. I put it back in, and it's clean. So bypass caps are very useful, right? And instead of using the two ROMs I had before, which were double leap ROMs, just as a test, I'm using slower EEPROMs now. These were 120 nanosecond response time. These two are 200 nanoseconds response time. They are ceramic EEPROMs, which can be erased through UV light. I covered the little window. So this circuit should work with these lower EEPROMs, because 200 nanoseconds response time, so together they would lead to 400. And I have more than 600 nanoseconds within each Cavia clock to do what needs to happen here. So this should not change anything. If they don't work, I just swap back the old ones in there, and the pinout is the same. So these are the changes. Let's see what happens now. Okay, fingers crossed. 3, 2, 1. Oh yeah. Yeah, this is it. That's the correct image. Let's test the stability now by turning it on and off a few times. You have to wait a few seconds for the capacitors to discharge so the power-up reset works. The same image again, so far so good. So it works perfectly. I understand why Cavia now is initializing perfectly. We don't have the little breadboard effects that were causing a failure of the power-up reset, and then the internal counters of Cavia would be starting in random states, and then you would get a random character order and random vertical alignment on the screen, because these counters were not initializing at 0. So I understand why now the character order is okay and the vertical alignment is okay. The screen starts with the top line of the first character line and ends with the bottom line of the last character line. So this is all explainable. There is one puzzle still though. I was also having problems with the initialization of SKANK. Sometimes it would initialize in a state that would stop the counters, and SKANK wouldn't produce the Cavia clock signal. And that happened, I don't know, once every 2 or 3 times that I power cycle the system. And it's not happening now, although SKANK is still on the adapter and not on a development board. When I put SKANK in the adapter and Cavia was on the development board, Cavia was still not initializing right. But SKANK does initialize right, although it's on the breadboard. It's a mystery I may not be able to solve, but then again, it doesn't really matter, does it? We know the chip works when Cavia is on a proper PCB, so it's safe to proceed now and do a proper PCB design for this video circuitry. The question is, will I do it immediately, or will I develop at least some of the rest of the system in order to get a first PCB that has a more or less complete system as opposed to only the video part? I have to think about it. Even with the breadboard circuit not doing a proper power-up reset, we still get an image. It becomes a stable image, misaligned, but it is stable. So we can make some measurements. What I'm measuring here is both the input pixel clock to SKANK in blue, that's the blue curve you see there, and in yellow it's the output Cavia clock as it comes out of SKANK before it is boosted by the buffer. And what you can see here, I placed the two cursors A and B in the moment, in the case of A, in the moment the blue pixel clock cycle crosses a certain threshold, and then I placed cursor B, which is not very well placed, to make a little correction. and then I placed it at the moment when the cavia clock in yellow crosses the same threshold. And what you see here is the propagation delay between the rise of the pixel clock, which triggers the cavia clock, and the moment when the cavia clock actually rises. And the difference between them is 15.2 nanoseconds. And that can be explained by the propagation delay. This is not the buffer, because I'm measuring it before the buffer. So this is purely the internal delay in SKANK between the time of the pixel clock rise and the time of the rise of the cavia clock. So this is purely the internal logic. If I move the yellow probe around to measure what is actually going into SKANK, this is just because the trigger now is on a channel that doesn't exist. So if I move this one around to see what cavia is actually getting, and I have to change the trigger again because the cavia clock is intermittent. It stops during the synchronization pulses and the front and back porch. So if I change that again, now we have to readjust the cursors. So I will move, B is okay actually, and then we adjust this one. Yeah, so what you see there is the delay is now 27 nanoseconds, and this extra delay is explainable by the signal propagation delay through this buffer. So here you see the pixel clock rise, the last pixel clock before the cavia clock rises, so it's this one, and the time it takes until the cavia clock passes the same threshold, and the difference between the two, B minus A, is 27.2 nanoseconds, which is not small, but in this case it doesn't matter because we have over 600 nanoseconds of time for cavia to do what it has to do before a new byte is latched into the shift register of SKANK. So this is just a curiosity. It shows you that signal propagation delay is a real thing. Right now, I don't have to be concerned about it, but there are many other situations in computer design in which this is extremely important. And this propagation difference of 27.2 nanoseconds is an outright killer in many applications. Not this one, because I designed it so it wouldn't be a killer, but sometimes you can't avoid it. Sometimes the only way to avoid it is to sacrifice performance, and people don't want to do that. And here's another interesting thing to measure. Now I am again in blue measuring the input clock signal for SKANK as it comes from the buffer, originally from the oscillator, and then into the buffer, then it wraps around and goes into SKANK here. And I'm measuring state S1 of SKANK, which is exposed to a pin because, well, one, it's free, since the logic in a CPLD is always associated with a pin, whether you put it out or not. And two, by exposing the states of the little state machine that produces the clock signals used by the shift register and cavia, it's easier to debug it. So what you see here in yellow is state S1, which provides the clock for the shift register. That's one before the least significant bit of that counter that works as a state machine. And then you see that one pulse of S1 is as long as two pulses of the pixel clock in blue, which is of course the way the thing is designed. S1 changes for every two pixel clock pulses in that counter. There is also a little propagation delay between the pixel clock pulse that should trigger a positive transition in S1 and the actual transition of S1, which you see here. I put the cursors A and B there again, and here you see that it's 6.2 nanoseconds, so less than the propagation delay between the pixel clock and the cavia clock that we saw before. So the lesson from all this is that if you're doing computer engineering, you cannot stop at the logic abstraction layer and only deal with ones and zeros. You have to imagine what's happened physically to all the electrons, where they are going. Are they arriving the right time, in the right place correctly at the same time or not? What are the phase issues? What are the power up and power down issues? So you have to think physically to get this right. I am satisfied with the work that has been done, although we didn't get a completely stable breadboard only prototype. To get it totally stable, we need to use the little development board from Microchip. But the prototype has served its purpose, which was to let us know that the design does work, and it certainly does. And we also know, based on the work done in this video, that it will be stable and robust the moment we move to a custom PCB. The question is still, when will I do that custom PCB? I think I will do some more of the I/O control development before designing that board, because I want a more complete board than one just with the video circuitry. There's nothing wrong with the latter. The video circuitry uses a much faster clock than the rest of the computer, so there's nothing wrong, there would be nothing wrong with building a board just for that. But I'm comfortable enough, I mean, there's no certainty in this engineering business, but I'm comfortable enough with the results we've seen in this video to wait a little bit more and get on with the I/O control part, which is a very exciting part. I have already been working on it, although I didn't make a video yet. It's coming soon. I thought it would be in episode 7. It's now postponed because of the little issues we found with the VGA circuit, but it's coming. It's very exciting. I want to do a little bit more of that, and then I will design the first prototype custom PCB so we can do some of the more, how to say, boring software development around the kernel. Stay tuned, more is coming soon. Thanks for watching. Take care.